right, let's get started. Can you hear me? Works? Works. Okay. Questions? Comments? Complaints? Nothing. All right. Yes.
About tomorrow's lecture, will it take place? No.
No, it will not take place.
Yeah.
Okay.
Sweet.
Yeah, next week we will certainly have a one lecture on Monday on the regular time, and then I will let you know what happens after that. Because I think that I will be able to cover up to LSD reduction formula proof. After this, if I have one more lecture, so we will comfortably cover. And the question is whether we want to have one more lecture either on like unitarity and optical theorem, at least to touch base. But fully to discuss unitarity and optical theorem, you need to talk about the loop diagrams and renormalization. But the qualitative aspect of that can be discussed, nevertheless, without actually zooming into the loops and you fight against the divergences. So, or another option that I'm thinking might be our TA, Yoho, great group theorist, can talk about the representation of Poincare introducing fermions and vectors to prepare you for the next semester. So then you will start combining things together to talk about quantum electrodynamics and all that. Okay? I will let you know. Any other questions, comments, suggestions? Okay. Good. Oh, awesome. Almost scary. Okay, so let's continue our discussion. So last time I established the following fact. So here I will give you roughly 5 to 7 minutes review of what we talked about, writing up the full board, and then we will go from there to start talking about to build up the formalism. We need to talk about LSD reduction formula. So we talked about the two ways. So we defined the two objects. One we just call this, and then another I call Z of F of the Feynman, meaning it has a interpretation in terms of Feynman's diagram, and this was defined by splitting the total Hamiltonian into rho dot phi, where we take this to be our base, and this to be our interacting part or correlation part. So then we look at a vacuum to vacuum transition in the presence of this source. Okay, so I'll put everything in hat. And then we were able to talk about expanding this minus I to the n or n factorial, and a whole bunch of integral, and then a lot of rows. So let me just write row 1 to n without. So this basically means the row of xn. And then we had this Green's function. And throughout the derivation, by doing the derivation, we were able to show that this Green's function is actually, oh, by the way, so in case you still care about that, there's normalization factor. So this was actually a time-ordered Green's function of full Heisenberg picture. So that was one side of the story. Again, there's a normalization. On the other side of it, we now split this thing slightly differently. So we took this and then combined this thing together. So now we took this as our base and this as our interaction or correlation that we want to expand over. Okay, and then we looked at transition amplitude or vacuum to vacuum transition amplitude in this split. So now you see that I'm seeing the full vacuum, interacting vacuum, because I took the base to be interacting Hamiltonian. So the vacuum associated with the base part. So it's full vacuum. Here is a free vacuum because that's our base. And then what we saw was that now we can also rewrite this by expanding in powers of a row. the same thing so that we can actually look at the matching. So then we had a big, sorry, let me first write. Okay, so let me first write the analogous of expression. So we can again expand in powers of a row, a lot of integrals, row, and the same so far. And then we have a Feynman Green's function. And then this Feynman Green's function, which now has explicit and straightforward interpretation in terms of a Feynman diagram extension, can be written as this. Now this is a 0, time ordering, and then e to the minus before x. This, so that corresponds to interaction picture, interacting Hamiltonian of only this guy. And then we have now interaction picture operator insertions. Divided by, just like normalization, here our normalization turned out to be this. I'm ordering. Good. So that's what we have seen. And then the interpretation of this thing was that now you're looking at the vacuum to vacuum transition without a source. So you cannot actually produce or detect a particle. So this turned out to be a bubble. And this one has, for all purposes of discussion, exactly the Feynman amplitude part. Okay? So basically, this is a diagrammatic expansion of a Feynman diagram without including vacuum bubbles. And then we saw that these two sides are identical. Okay? So that was the establishment we made last time. So this does not rely on any notion of perturbation theory. These do rely on the notion of perturbation theory because I'm assuming there's a splitting of this part. Okay? So for any perturbative QFT you can take, you can start out either from here and then you can define a Green's function, which is a time model correlation function of Heisenberg picture operators, which can be interpreted as a Feynman diagram expansion. So that was the establishment. Okay? Good. So let's continue from this point. Yes.
I have a question on the vacuum bubbles.
Okay.
It seems that the first definition of the generating functional, the denominator, it seems it does not include any vacuum bubbles as there's no integral of
This part.
Yes.
Uh-huh.
It seems that it does not include any vacuum bubbles as it does not include any time propagation, time evolution operator. But it is included in the Feynman generating function also. Is the physical vacuum can I think the physical vacuum as the vacuum bubble included vacuum?
Okay, good question. So you're asking, given this correspondence or equality between these two,
Yes.
what is the physical picture of this thing?
Yes.
Right? Given the fact that we have this picture, like there's all the vacuum bubbles. So to answer the question, so let me give you some idea, but I'm not sure if I can fully justify the question. But we have seen that this denominator part in the limit where time goes to plus minus infinity can be expressed as basically something that looks like this factor and then this factor, right? So we use the vacuum saturation trick. We first rewrite this in terms of time evolution operator from t minus to 0 and the 0 to t plus. We took the limit and then we saw that it collapses to this, basically, right? So insertion of a complete set of state, only vacuum survived. So that's what we did. So good. So now let's take a look at this and we can ask what is the relationship. So this part matches here, right? That part matches, and then basically this part of the overlap in the large T limit sounds like what it does all this sort of vacuum bubble business, right? So if you try to compare these two, okay, so that part matches. Looks like the difference between naive, so vacuum bubble is basically in this overlap between the free vacuum and then the full interacting vacuum. Now, if I may translate this into physical term, physical language, the free vacuum, absolutely no excitations, nothing is possible. Suppose I give you free theory, no interaction at all. You can define free vacuum stays as a free vacuum, nothing happens, right? So only the propagation is possible. Now, if I include interactions, then if I say, oh, I had a vacuum, that free vacuum can do pair creation and annihilation again and again and again. Because of interaction, I turned on. You know what I'm saying? So the difference between this and that sounds like, to me, the vacuum bubble diagrams. So in the free vacuum, no, very clean, silent, nothing. But here, even though it's vacuum, you can still do this all kind of vacuum bubble stuff in the vacuum, true vacuum. So yes, probably along the line what you were trying to think, I would sort of agree to you that that might be the difference between these two. Did that answer your question? Okay, good question. Any other questions? Okay, good. So now let's move on. Okay, so today I want to sort of prepare ourselves so that we can talk about eventually how to express. So the second question, if you remember, okay, was how to extract. S matrix from this function. Now we know we can express this diagrammatically. But also we do have a non-perturbative definition of this object. Okay? So now let's ask, how do we extract this observable S matrix? So let's recall, to sort of build up, let's recall our baby version. Okay? Based on the tree-level intuition we just built up. If you recall, what we said was, okay, when we first defined the Green's function, or more precisely, just momentum space version of this object, we say that, okay, I'm just going to define this as a sum over all kind of diagrams, including external propagators, right? That's what we did. And then letting the external leg to be on off-shell possibly. That was basically an operational definition of this object. Even though now we have very rigorous definition of that object. Okay? So then we say, okay, because I have a collection of diagrams with all the lines, possibly off-shell, including propagator, we can get to the S matrix by first stripping out all the propagators of external legs. So the picture was this one, possibly have all the, including propagators of these legs. So we should sort of strip out all the propagators. It's called aggregation, horrible word, but it's pretty good word. I mean, the proper word, I would say, unfortunately. And then we put everything on shell, right? That's what we do. So we can get this by going from all external x, and then we're gonna impose on shell this after we sort of taking out all the propagators, right? So remove the propagator, put them on shell for all the external x. Then we get us diagram, which we sort of define how to compute the S matrix. Okay, so that's how Feynman diagrams and Feynman rules were originally defined, as if you recall our discussion. So that's the question. So how to extract the Green's function? Now let us also recall the following fact. Okay, so this object, the Green's function, now very cool object. So from now on, I'm not going to worry about the vacuum normalization, so I'm just going to drop the norm of the vacuum part, okay? You know what I mean. So this is defined in terms of Heisenberg picture sum operator. And if you recall, So this object, algebraic picture operator, first of all, not necessarily, in general, it's not a free field. Okay? And even more so, this may not even be any one of sort of elementary field appearing in Lagrangian, for instance. Even if we talk about the perturbative quantum field theory, this object, the way it is defined, may not even be one of those fields appearing in the Lagrangian at all. So meaning it can be some composite operators. Okay, I can smash them together, several operators, and putting them and zoom to the, them together as single space and point, we can define some composite operators. And if you also recall, this object can, for instance, generate or create not only one particle state, but also, in principle, some multi-particle state, or maybe it can even do a bound state. So we are being very general. We were being very general when we define this object. So therefore, if we want to answer this question, in order to answer that question, we need to know. So this is, for instance, in the picture of S matrix, these external legs are actually asymptotic. One particle state. Okay, so in this S matrix picture. So if we want to talk about smashing together, actual elemental, like actual one particle state together, and then have some interactions, and then another set of a free particle state comes out, we need to know how to get a one particle state out of this general operator. Okay? So one step towards answering this question fully is therefore we need to understand, how to project this quite general operator onto one particle sector of field distance. Okay? Only then we can start thinking about the S matrix. Is that clear? Is the question clear? Because this can do a lot of things. But in the context of S matrix, we are interested in a product of a one particle state. So what's the precise connection between this rather general operator to one particle state? That's what I'm saying. Okay? We need to understand that. So therefore, let's just recall a few facts about what we are doing. So first of all, let's first think about the vacuum quickly. So this is a full interacting vacuum, and then the way we sort of introduced that or defined that was that this carries no energy momentum. So in terms of energy, it is the lowest energy state. And then again, from now on, we're just going to take unit norm. And then, so one particle state, we will just label as some momentum, either P or K, whatever notation. And then we will normalize as usual. And so far, nothing different. So to understand how this thing behaves in each of the sector, so let's actually talk about it. So in the context of the vacuum, let's look at this. So what is the vacuum matrix element of this operator? Okay? And then we're going to also ask the same question for the one particle state. We will also ask the question of multi-particle state, for instance, right? So let's first talk about this. So first of all, let's use Lorentz invariance. In this case, really translational invariance. So this operator can be written as P dot x vacuum. And the vacuum, as defined as in number 1, doesn't do anything, so you can easily establish the fact that this. And you shouldn't be surprised. We are dealing with a scalar, and this equation just tells you that the vacuum expectation value of this operator, whatever that operator, is a translationally invariant. It has the same value at x equals to 0 or any value of x. That's what this thing is telling you. And we are going to work with an assumption that this thing is 0. This is an assumption. Okay? So that part is an assumption. And you can ask, okay, what if I have to deal with the quantum field theory where this is not true? Do I have any hope to use any of the discussion we will make from now on? So in that case, what we're going to do is the following. So suppose I have a situation like this. So you will eventually talk about this. So here I'm drawing a field space. Okay, so these are field space, and this is, if you like, a potential direction. So in this case, you see that the vacuum is. So in this picture, the vacuum is here rather than here, right? So in this case, actual vacuum expectation value, meaning the actual vacuum value, is sitting in here. So let's write this, which is not equal to 0. And in this type of examples, which you will learn eventually, a phenomena known as a spontaneous symmetry breaking occurs. So let me just tell you in words. Okay, I'm not going to develop the machinery for now. If you have a theory that respects a certain symmetry, the theory is invariant under the symmetry. But a state may not respect the symmetry. For instance, the desk is a state of concurring invariant quantum field theory. And this thing doesn't respect the rotation invariance. Look at it. And you are a state which doesn't respect a translational invariance, where you're not there when you are here, for instance. So state keep right. And when a particular state known as a vacuum does not respect a given symmetry of the theory, we say that that symmetry undergoes a spontaneous symmetry breaking, and there's a consequences. Anyway, so in this case, so you want to develop your quantum field theory, especially perturbative field theory, with respect to this vacuum. Okay, you first go to the vacuum and then ask, what happens to small perturbation with respect to that? You want to study the physics of that. So you see that now we can parameterize. For instance, when this thing does not have a 0 vacuum expectation value, so then I can split this quantum field with respect to its vacuum expectation value, and then small fluctuations. And this small fluctuation with respect to the vacuum expectation value is guaranteed to have a 0 expectation value by construction, because I subtracted off that. So I'm telling you this, so we are going to deal with a situation where the field operator, again, this may not be a free field or even elementary field, but whatever operator that I'm talking about, we are going to work under the assumption that it has a 0 vacuum expectation value. But I'm telling you, if that is not the case, you can always just subtract off that thing and redefine what you mean by your field operator in that case. Okay? So without loss of generality, therefore, I'm just going to take this as a working assumption and move on. Okay. So that's the vacuum story. What about the one particle story? So let's actually now ask the following question. So what about this? So I have a one particle state, and then take this a pretty general operator acting on the vacuum. So I want to ask this question. Okay, so this will be and then again using the translational transformation property of this operator, you can rewrite this as e to the I x. And then you can quickly convince yourself that this will be p dot x with okay, so that phase basically saying that this comes from translation, and this quantity may be called a one particle matrix element. Basically, you're asking, okay, what sort of business this operator can do for me? Does it create certain state out of the vacuum, which has a non-zero overlap with the one particle state or not? Right? So if somebody hands you a random operator and you check this, if this is 0, that operator has nothing to do with the one particle sector of Hilbert space, because it cannot do anything about the one particle state. Okay? So when this is non-zero, you're on business in the sense that that operator can now touch the one particle sector of the Hilbert space. Okay? Now let's do one thing. So that's the one particle matrix element. Now note that we are dealing with a Lorentz scalar operator. Okay, that's what we're doing, and this should be a function of a momentum, right? Such that it's Lorentz invariant. So this should be some function of momentum which is Lorentz invariant, so Lorentz scalar. And since you have only a single argument, the only Lorentz invariant you can construct out of the momentum is it should be a function of p squared. And since we're talking about specific one particle state, that should satisfy this dispersion relation or on-shell condition, which means that this is constant. So what it means is that for any given one particle state, this is a constant. So let me call that constant. So let me just call that constant, define the constant to be maximally confusing way. So you should never call this thing. So square root of the z. Because what z are we talking about? Exactly. Which z are we talking about? Well, I just introduced a new z for you. So we had a partition function or generating functional, right, of one kind. We introduced another generating function of Feynman kind. This has nothing to do with any of them. And people like the z a lot historically somehow. And they use the z for generating functional. And this quantity, even for this quantity, you will have a z 1, 2, 3, whatever number you like. So this is nothing to do with the generating functional. This is encoded fact that this is a one particle matrix element of a random sum operator, not necessarily elementary field operator. We call this. And then there's a name for this. So this thing is called, historically, wave function renormalization constant. You will learn much more about this next semester. Okay? But as Coleman stated correctly, really you should have called field renormalization constant. That's what wave function are we talking about? Okay? So good. So if I have time today, I will provide a alternative viewpoint about this factor, constant factor. Okay? It's known as, I call it Riemann spectral representation. So if I have time, I will go through the argument to show what's the connection of these constants in that context. More general in non-perturbative sense. But for now, hopefully you understand that whatever operator you are given, if it does have a non-trivial overlap with this, provided this is a scalar operator, this should be constant. I'm just defining a constant. That's all. Okay. Yes.
In that formula, are you meaning that
Which one? Here?
yeah, any field must have the same sandwich between sandwich of the vacuum field of some vacuum state. Any field must be constant.
No. So you're questioning, should this is a scalar. I'm using the fact that I'm looking at a Lorentz scalar.
But you use just translations.
Yeah, but sorry. But then if this is so I'm just using the fact that this field translate like this.
Yeah.
Okay. And if it is not a scalar, you can think about what happened to that. And it may not be, if you have a directional information. That's one of the reasons why spin-the particle should never have a vacuum expectation value, because it will break the translation. Yes. So I'm using strictly a scalar field that satisfies this, and then it has to satisfy this relation.
For the case of the scalar field, that quantity we often call the classical field in the effective field theory.
You can call it classical configuration.
Yeah, but you mean that was the space-time in the kind of
For scalar.
what about that?
If you have a scalar that has a certain configuration, say soliton, it will break translation invariance.
How can you prove that?
Say it again.
Because you don't use any fancy thing, but you just assume that field is a scalar field. Then how does the instant soliton come?
How does the soliton come in? So this is a field operator, and soliton is a solution to the classical equations of motion, right? It's a solution.
Yeah, but I know that the classical configuration, if some classical configuration of scalar field is space-time independent, we call that classical configuration as like soliton, right?
So if you like, I'm looking at the vacuum sector, right? I'm looking at the vacuum sector, and then if you have a soliton sector, they are separated from this vacuum sector by a certain topological barrier, right? That's how they are defined.
Then in that case, the vacuum is not unique.
No,
So
so
state.
Huh?
The state is not unique.
vacuum state. I wouldn't say that. So given a quantum field theory, so let's just talk about scalar field theory, and then let's talk about the case where we have a kink, okay, or vortex. So then I can look at the sector where there's not any vortex at all. It's a vacuum sector, and then I can talk about this fact. This is a separate question. I can talk about this fact, right? And that sector, I can talk about the excitation with respect to that vacuum sector. So that's the ground base for the perturbation I can talk about. And then we call whatever excitation on top of that vacuum configuration a particle. And then I can talk about the one vortex sector, which is infinitely far away from the vacuum sector we just talked about.
Yeah.
There's a topological barrier. It costs infinite action to pass, to go from one to the other, right? And then there I can take my base as a solitonic configuration, as a classical configuration. Okay, and then I can turn on the excitation on top of that too. There can be zero mode, there can be higher mode, I can talk about that too.
Yeah.
So I can quantize with respect to certain soliton configuration, I can quantize with respect to vacuum configuration. I'm talking about the vacuum sector physics.
In that case, the correct some state, 그러니까 오메가 스테이트라고 써져 있는 vacuum 스테이트인데 그 솔리톤, 그러니까 그 클래시컬 디퓨전 모션을 따르는 어떤 솔루션이 있고 그거를 그냥 예를 들어서 파이 CL이라고 부른다. 어떤 스테이트가 있어서 이거를 파이 텍스처 X에다 취했을 때 그 필드가 되게끔 하는 이 스테이트가 갖다가 솔루션이라고.
Well, okay. So here, so let's talk about the perturbation here just to be clean, and let me just think about this as a free vacuum, and that makes sense because the vacuum is your base. In this sector, the base is a vacuum where there's nothing, no soliton, nothing, no particle, nothing, right? And then on top of that, we are building up a quantum excitation. If you want to talk about solitonic sector, right? I mean, the vacuum there is the soliton. So the ground basis is the soliton configuration. right? You have a soliton, and then you can talk. So it's just like you have a nothingness as your basis for your quantization, and then on top of that there is a wiggles. That's a particle. Then we'll talk about the scatterings on that. If you want to go to the soliton sector, no vacuum sector, the ground basis is your soliton configuration. It's like water wave.
What is the first one is T? That is T.
What is the back? Soliton is the basis.
The lowest density of that sector is
Soliton.
solid.
Yes. You're on the monopole. That's your basis. And what is the like base energy of the base state? Monopole mass. And then on top of that you can fluctuate. Sometimes you can go from one sector to the other if there's a interaction that breaks the super selection rules. Okay, but the two leading order, there's a vacuum sector, nothingness, there's a fluctuation called the particle. There's a soliton or whatever, topological object, that's the base. And then the action of that quantity give you this amount of energy stored in that sector as a bare minimum. And then if you turn on extra wiggle on top of that, some of them cause energy, some of them does not cause energy, called the zero mode. And then there's a classification of those sectors according to the topological charge. Okay, good. Where were we? So yes, we just talked about the vacuum, and then we talked about this particle. One particle sector, and then I just talked about this one particle matrix element, then showing the fact that this should be basically constant, because I'm talking about the Lorentz scalar operator. I just defined that constant I will call square root of z, okay? And z is just a number called a waveform renormalization constant, or the field renormalization constant, okay? Good, so that's where we were. Let's continue. Okay, so then I will introduce a renormalized, even though I never talked about beautiful. So renormalized field. Either renormalize the field or the operator, whichever way you like to call it. So I want to define the following way. So here, P of the starting point with a vacuum is square root of z. So I want to define and rescale the operator, which I call a phi sub r for the renormalized, such that it is 1. And you clearly see that the relation between the two is phi square root of minus half is phi r, right? Just divide by that. What is the benefit of doing that? Well, in that picture, if we look at a 2-point function of this renormalized field, okay? So benefit of doing that, but restricting myself to the one particle sector of Hilbert space. Remember, this can do many things. So I'm just restricting myself to the one particle sector. Then, in momentum space sense, then this will satisfy a clean form, which is the same. So it takes the same form as a free field. Okay, so that's the benefit. And eventually, in the story of a scattering matrix and so on, it turns out that it is useful to use renormalized field. Even though you can do everything also in terms of that, but just for the sake of usefulness and efficiency, we're going to just use this renormalized field. Okay? Okay, so then one thing that I have to say here, let me just do it here. So we are talking about one particle state, and that one particle state, so here there's one particle state, let me just write here. We'll have energy, for instance, according to obviously this formula. If I say how dumb the expression it is, well, why am I even writing this down? It's taking 5 seconds to do so. This is because I'm not necessarily thinking about perturbation theory at the moment. right? I'm talking about probably horrendously interacting field theory. So therefore, when I say mass, I mean exact physical mass. Whatever the particle, it will have the exact mass. And that mass can actually be different from whatever mass parameter you see in the Lagrange. So for instance, in our scalar field theory, for instance, we could have write down something like this, right? There's a mass parameter. We discussed why this text is an interpretation of the mass at all and so on and so forth. But the actual mass, so let me just put a P to denote it's a physical mass, can be different from this because of quantum effect and so on. Okay? So for now, I'm just saying this. So therefore, when I say, therefore this quite general operator restricted to one particle sector can take this, once we just do this rescaling or renormalizing this constant, this will have exact whole mass. Okay? If I have a chance, I will try to connect between these two. But we'll see. Okay, good. So let's continue. So that's a renormalized field. Now let's talk about scattering. So to talk about the scattering, I want to introduce normalizable, meaning well-defined, wave vector states. So which I will denote it as F. Okay. So let me first write the expression and then let's talk about it. So this is the sum over K. So what I'm saying is that this is actually this represents a plane wave state, right? Because that means that this is a momentum eigenstate. And then as you know, if you project it onto the X, meaning to look at the wave function of that, it takes basically this. Okay, so this is a plane wave. And plane wave being delta function localized in the momentum space, this is infinitely spread in the Gaussian space. And you cannot talk about the scattering with the plane wave, because if you have two plane waves, necessarily they already have overlap, right? Even before they get close to the interaction point. So it's hard to even talk about the scattering process. So therefore, I want to design a profile by performing proper superposition of a plane waves. I want to basically produce something that localized, okay, in both momentum and also especially a Gaussian space. Okay, so I want to have a bundle that moves. So given this, you can do straightforward thing. So you can define a wave function or just a state, wave vector state. That will be obviously so in this picture, in terms of this wave function, this is a proper superposition of a plane wave. Okay. And if you don't like this factors 2 pi to the cube 2e, that's precisely because I normalized my one particle state, including all those factors. If you look at the inner product, that's why. And you can also try to look at what about the momentum space wave function of that state. Clearly, if you hit this, you get a delta function, but also collapsing all these factors. You should be able to check that this will give you a prime. So this is nothing but a wave, if you like, profile or wave function in the momentum space that it should be. Okay, so now I have wave packet. Now we will do a series business. So now, really the question is, I think I have written down, given this operator, I want to project this operator onto a one particle section. At least we have checked. That if we assume it has a non-trivial overlap with the one particle sector, we know how to define wave function renormalization and so on and so forth. But given this operator, what is the actual operation you have to do to actually project onto the one particle sector? Okay? So that's that. So to do this, I want to state one fact. So, by the way, here I should have said the following. So when I say this, obviously since this, each of these plane waves solves the Klein-Gordon equation. This also solves the Klein-Gordon equation, right? So what that means is that, so that thing, here, let me write, because we're gonna need that also. So this solves the plane wave, this solves the Klein-Gordon equation, but this, if you look at that expression, corresponds to positive frequency solution to Klein-Gordon equation, right? So I'm only summing over positive frequencies. Okay. Good. So given this, now I want to explain to you how to construct the projection of this onto one particle sector with, for instance, one particle state, if you like, which is this profile, particular wave packet structure. Okay. So that's what I want to talk about. So to do this, I want to note the following thing. So given a well-defined, smooth, and so on operator, I'm not even specifying what operator, some A of x. And for now, I'm just going to assume that this operator is Hermitian, because I want to talk about some observables. Okay? And we know what happens if that's not the case. You can always construct a Hermitian, anti-Hermitian, and so on. So let's not worry too much about it. So given that, the following statement is true. Let me write and then explain. So, which we will see how to see that. But let me just phrase the fact. Suppose you have an operator. Okay, you have an operator A. Eventually, we will take phi r, the renormalized operator phi r, given an operator, and then suppose you want to somehow construct an associated operator, okay, which is intrinsically tied to this one particle wave packet state. More precisely, eventually you will see that I will construct an associated operator of a phi r, which I erased, okay, such that it knows about how to only create a state associated of f of x wave packet and nothing else. Okay, so that's where we are heading. Remember, I want to be able to define asymptotic state starting from pretty general operator of phi. So I want to just project onto that. If I specify the wave packet state, so suppose I know you can produce that guy, but can you turn into something else so that you only know how to produce a wave packet state in far future or far past? That's the command I'm doing. I'm saying this achieves the sort of a projection job. We will see some other version of proof why it does the job, but for now, this is a general statement. Given a solution, positive frequency solution to the Klein-Gordon equation, if somebody had you a Hermitian operator, then if you do this job, integrating over the whole full space and time, somehow you project it onto this object, which is written this. Okay, it's something like commutator of A and Hamiltonian, if you wish. Okay, with that profile function. And now I will show a nice property of this. So if we take, instead of saying a lot of words, let me just take this to be our field operator. Okay? So then we will have associated phi r of f object, T, with the following property. So property number one of that object, so induced operator, is that the vacuum expectation value of this thing is 0 if and only if the original operator has a 0 expectation value. So this is just a simplifying assumption. Okay, we don't have to spend too much time on this. But second, and crucially, if I take a one particle state, and then if I use this guy, starting from the vacuum, so somehow I'm creating a certain state, and then I ask, what is overlap with this one particle state? So the fact that I'm asking the question in the one particle sector means that I'm asking, what do you do in the one particle sector of Hilbert space? Okay? And then you will see that this is equal to this, which means that now this operator turns on and create a one particle state associated with that wave packet state. Property number 3, let me just continue. So if I instead ask any multi-particle state, and then ask, what do you do? What can you do there? Now I have to do one job, which is, if I take that time to either plus or minus infinity, you get 0. What that means is that asymptotically, this induced operator is completely blocked from the multi-particle sector of the Hilbert space. Okay? Again, asymptotically. And then another fact. Now, if you ask the following question, so now if you ask the question, what about this? So I understand that you are a creation operator. So this first fact tells you that this thing is a one particle, not just anything, but creation operator. Right? Because it creates and then has a overlap. You can ask, are you also an annihilation operator? So now I'm going to be agnostic whether psi, it can be either, this can be either one particle state or multi-particle state. Okay? So we will do demonstration soon. And can you also be an annihilation operator for the one particle sector or multi-particle sector? So in all of those cases, if you take this limit, we will find 0. So what it means is that this construction, which you obtain by performing this, some mysterious projection, you get an induced operator out of any this general operator phi bar, which is exactly just to do a creation of a wave packet state and nothing else. Okay? So I'm going to prove this, but before that, hopefully you see why we want to have an object like this, right? Because starting from the Green's function, which is a time order product of Heisenberg picture operators for any operator, some certain operator, right? Then if you know how to zoom into a sector, which knows how to create asymptotically wave packet state, then you can take that zoom in projection operation to connect each of those phi of h appearing in the Green's function to asymptotic state either in the far past or far future, right? So if you go through that projection, the leftover piece will be a asymmetric eventually. Okay, so that will be how LSZ eventually works. So this is the first step towards that. Okay, so now I'll just go through dumb proofs of this fact. Any question before I do?
어심토틱하게 하는 게 최소한인가요?
Asymmetrics is defined asymptotically. Asymptotically in a sense that given a localized interaction region in the space and time, if we can have a state which is separated far enough from the interaction point, and also far enough among themselves that they don't have any interaction, okay? So that I can now have naive picture that I had two completely non-interacting initial state, and they get close to each other, and then going through some process, and then producing some other particle, again, going far away from each other. So, in a sense, asymmetrics itself, and the scattering amplitude is defined under this picture. Any other question? Okay, so let's see. So that spend your time thinking about it, just do something. And I'll just start from the second, okay? So second, I can actually combine with the third together, and then we can demonstrate. So so consider a fixed a state psi. Again, this can be either one particle or multi-particle. And then I'm not gonna specify until I need it. So let's just consider one thing. And then let's just ask the following question. So psi pi over r t factor. Let's just compute this explicitly. Okay? So let's just use the definition of this induced operator. This. And then I have a psi. And then I have a phi of r time derivative of f minus f time derivative of phi r factor. Now here, this is just a function, right? These are just function. So I can rewrite this as this. So this minus this, and then vacuum expectation value. Now this is x. Okay, so far so good. I just literally plugged in the definition. This is a function, so obviously I can nothing happens. Okay, so this again using the translational property, I can rewrite this in terms of phi r0 with 2 exponential. So that will give me e to the I p of psi, the momentum associated with this guy, x psi phi r of 0. And this object, if this were one particle, obviously this is one particle matrix element. If this were two particles, this is a two particle matrix element. So this is psi matrix element, whatever this is. Again, I will be agnostic at the moment, okay? But later I will constrain myself to the one particle sector and the multi-particle sector separately. See what happens. Okay. So let's just continue our calculation. So we can just do it. And what was this? Did I erase? Did I? I did. Correct. So what was that? You remember? F of x was a wave packet, right? Wave packet. So 2ek some profile e to the minus ik by x. Okay? The linear combination of a wave of plane waves. So if you take that, you get minus iek. Remember, this is, I said, this is one particle energy of the one particle state. Okay, ek, because this is explicitly one particle state. And what about that? So that gives me minus, and then
EK F-라고 써야 될 것 같아요.
sorry?
EK F2가 들어가야 된다면.
I will do it. I'll put it in. That's not what I was worrying about. I'm worried about if this was a plus. Plus. Okay? So then if you do this, if you take a time derivative, what do you get? I, energy of whatever the psi state. Okay? And then I have overall F. So I have a gigantic expression I still need to do, which I have to do. I cannot avoid. F, okay, good, I have done that. And then I will have this exponential factor, which is, oh, interesting. Interesting. You know? Interesting. No, I think this was minus, but then how come Okay, let me finish up. So let me go with the minus sign for a second. Interesting. K minus psi at x. But then if I switch that to the minus, obviously I will have a minus here, right? And then and so on. Okay, good. So then what we'll have, I will have is this. Okay, so are you with me so far? No, this is right actually. Thanks. This is actually right. Okay. Good. I just literally plugged in this thing, and then I just computed it. So think about it, and then I will continue here. Good? Good. So let's do the following. So let me rewrite this as follows. So I'm about to do this d3x integral over this guy. Okay, so let me just do it right away. So if I do this, what do you get? This is an integral over 3x. This is a four vector contraction. You should get 2 pi cube delta k minus p psi. But then there's a leftover phase, right? So the zeroth component, that's I ek minus p psi k. Are you with me? Now this is a key expression, but let me clean up a little bit and then we will look at it. So therefore we get I and the overall minus I, so they all cancels out. And then I will perform this delta function also. So I'm gonna just use this to collapse this. So what I will have is this ek plus e psi. Okay, so that's so far so good. And then I have minus I, ek minus e psi t, and then the matrix of
FP 사이가 남지 않나요?
Oh, sorry. Yeah, thanks. I still have this. Now this should be replaced with the p psi factor because of the delta function. Okay. Good. So far so good. Okay.
K에 integration 다 하는 거예요?
Oh, yeah, yes, I already have done that. So I had a delta function after d3x integration, and then I used the d3k to eat up the delta function. So I'm left with the 1 over 2e, and then this factor, collected this, and then an exponential factor, and then factor's element.
그 아래에 있는 K가 없는 것으로 다 쌓이는 거예요?
So yes, this should be p psi now. Yes, you are. P psi, but corresponding to the one particle energy. Okay. Any question? So every single location you should understand it. Remember, this is energy of an arbitrary state. It can be 2 particle, n particle, million particle state. This energy that comes from here and then the exponent, that is specifically 1 particle state energy with the momentum p psi because of delta function. Okay? So even though they may have the same momentum, 3 momentum, they may not have the same energy. And in fact, that's crucial, as I'm about to say something about that. Okay? So for now, I want you to understand the notations. Specify your state. Okay? So this is energy of that state. This is 1 particle state energy. In fact, not just 1 particle state energy, this is a wave packet energy with the 3 momentum. This is the profile, this is the exponential factor. Okay. Now, I can just argue this 2 and 3 right away. This is a crucial moment. And now, you probably want to listen up, because now you will see how the projection happens. Okay, this is the key moment, how the projection happens. So now, let's consider this to be one of the one particle state. Okay? Now I'm taking a one particle state. Then several things happen. First, crucially, so let me actually write because this is very important. So number one, what happens is that the exponential factor E this minus E psi, again they are subtly different, become exactly zero, even before I take any limit. No, one with this one. One, because this is the same, right? Because this is the same. That's one. Two, what happens? Therefore, because of that, the prefactor E P psi plus E psi over 2E P psi becomes 1. And therefore, 3, after that, what you're left with is literally f of P psi, and then now this is just the P psi, right? This is one particle state. Second. Yes? So that's what you get if you identify this is a one particle state. Okay? Now, does this answer the question that this actually collapses to this? So, what is this? This is precisely the state associated with a one particle state with a momentum P psi. Or more precise, this is a wave packet associated with a momentum P psi, right? Summing over that. Yes? So, okay, for now, let me stop here, but let me now argue exactly what happens if this is a multi-particle state first. So if this were multi-particle, first of all, the crucial difference happens. This is the most important part. Now, this is always negative. So multi-particle, let me write even in red. Now, P psi is always greater than P psi. Remember, this is the one particle energy. This is multi-particle energy, but with the same free momentum. What that means is that this phase never dies out. And then, if you take a large T limit, again by this vacuum saturation trick sort of a structure, that thing goes through wild phase oscillation, everything dies out. So this kills everything. Forgetting about even prefactor, that's just it. So for multi-particle state, this overlap goes to 0. If you like, you can do the following trick. So in this exponential, if you like, if you want to see explicitly, let me just write this, and then you will have infinite. You can turn on proper again, probably plus minus I to 1, okay, to see why it goes away.
사실 멀티파티클 스테이트면 P psi는 그 여러 파티클 모멘텀의 합인 건가요?
Yes. In case you're not convinced by this, think about it. So think about two particles. If you have a two particle, and then you want to construct a minimum energy configuration. So in this case, total energy is energy of this guy plus energy of that guy. So to minimize that, you want to have a minimum total momentum. So total momentum is fixed. Because I'm constructing an energy with a fixed 3 momentum. I'm comparing to the one particle state energy, right? So with the given total momentum, I'm just governing, and then I'm telling you what will be the momentum configuration that give you minimum energy. That's when they go parallel. So for instance, half of momentum of each. But because as soon as you're killed, so the other extreme limit, they go backward. Suppose this is the original P, this should be the 2P, for instance. Obviously, you're jacking up the energy. As soon as you're killed, you start increasing energy. So this is the minimum, and if you can check that even in the parallel limit or collinear limit, this is true. Okay? Basically, you have a rest energy. This compared to that single factor. Okay.
근데 이 사이의 토탈 모멘텀 제곱 더하기 m 제곱의 스케일을 쓰셨는 건가요?
You mean this?
Yeah.
So if we talk about multi-particle state, this will be sum over energies of each particle such that the sum over 3 momenta of n particle add up to whatever the momentum p psi.
그다음에 저기 왼쪽 거는 p를 다 서미션 한 다음에 그 제곱 푸는 거죠.
Yeah, this is just the one particle but carrying that the same moment, 3 moment. So this is literally square root of m squared plus p squared. This will be sum over energy of each guy such that the sum of 3 momentum add up to whatever the momentum associated corresponding to this momentum. And I was telling you the minimum energy configuration will be when they go parallel.
저거 그러면 그거가 같은 거
Sorry?
그거랑 같은 거 저 등호가
You can check. When they go parallel, are you claiming when they go parallel it will be the same?
네
No, you can literally check. Just compute.
질량이 없으면
Sure, but here we consider gap systems. Yeah. Any other question? So let's wrap up of this part of the discussion, and then the last one will be quick. Basically, few modifications. So we take this somewhat mysterious looking induced operator, knowing that it has at least overlap with the one particle sector. Okay, and then we literally computed it, and then we arrive at this point. So for one particle state, so if this were one particle state with the wave packet, then this collapses, this becomes 1, and then we ended up having only this with that one particle state momentum, like a plane wave factor, so like this. And then what was this for one particle state? If this were one particle state, what was the answer for this? How did we define our renormalized operator? I defined the renormalized operator such that this is 1, right? That's how we introduced the wave function renormalization factor, and then we introduced the renormalized operator from a 5H. Okay? So, therefore, for one particle thing, this is just literally that. And if you recall, if you had a F here, and then if I look at a certain specific momentum thing, this was a wave packet such that this is a wave momentum space wave function, so that was precisely f of k. Oh, sorry, in this case, f of psi, cube psi, right? So we got that answer. So that this confirms the fact that indeed that induced operator, given one particle state, out of the vacuum, create such that it is actually precisely the wave packet state we created. Okay? So as time goes to plus or minus infinity, this particular operator actually can create a wave packet state. And then this part of the discussion showed that, on the other hand, it basically does not have any access to the multi-particle sector because of this projection. Now, if you look back, if you want to build up some intuition, I don't have a vast, deepest intuition yet, but if you look at this, and I don't have much of a good intuition on this picture, but here I do have that. Why you want to design something like this, right? And best way you can project out certain sector, and what distinguishes many particle versus one particle state? It is a difference of the energy given the same momentum. So then you just design this because these two factors precisely create an exponential of one particle momentum, full momentum, minus full state momentum, with the crucial factor of a minus sign here. Okay? Because only then, so because of this particular, in other words, if you had some star here or there, things will change. In that case, you will have a plus sign here, for instance. And then you make use of the fact in the large K limit, because this survives, creates a wild phase oscillation. If you are not in the one particle sector, you can actually project it out. Okay, so that's the basic, sort of a bit of intuition I can gain from this thing after doing this exercise. Now, let's actually knock out this thing, because we basically have everything written on the board. So, if we look at the other way around, so suppose now I'm looking at this thing, psi, okay? What will change? Well, so now this will be vacuum, this will be the wave packet state. And this will be vacuum, this will be wave packet state. Now, starting from here, you will have a sandwich of this guy, e to the plus IPX, e to the minus IPX here, right? So in that case, you will in fact pull out e to the minus I p psi x. Are you with me? If you flip the order, e to the minus IP dot x, so then if you combine with this e to the I minus IKX, what you get is you actually get plus sign here. Okay? And then obviously there's a flip, but that's not the crucial point. And then there will be flip here too. Also, that's not the crucial point. Now, with this, what you get is that regardless of the sector, you will always have here plus sign. Even if this is a one particle sector, you will still have this sum rather than the difference. Okay? So now, in this case, you don't even have a chance to make this phase to be identically zero, even if you are in the one particle physics sector, one particle sector. So in the time, large time limit, again, this goes to zero for everything. So that's why you get this answer, regardless of whether this is a one particle versus a multi-particle sector, and use a completely projectile. Hence, the conclusion is that this operator acts as the only creation, not annihilation, of a specified F, the wave packet state, one particle wave packet state. Okay, is that clear? Good. Now we know how to reduce arbitrary operator phi, or H or phi bar, onto one particle. Now, if we have a string of a Green's function, so it's a Green's function which is a string of operators. Let me use that. I'm done basically. I'm just anticipating. So now I know how to collapse this to each of the one particle sectors, right? If I use these projection operators. Okay?
Are you using the...
No, I just wrote this because you might be more familiar. I can start a bit off, if that was your question.
It only works for the scalar field, right?
This is a scalar field.
But you mentioned that can be any field.
Any field in the sense that Lorentz scalar, but not necessarily elementary or field appearing in the Lagrangian. It can be composite operator or scalar operator. That's what I mean. So then I know how to reduce this down to this guy, right? And then some of that I can take the time plus limit. Some of that I'm going to use as a minus limit. So this will get me asymptotic in state. This will get me asymptotic out state. But then in doing this, I need to insert this object. And what is that in the momentum space? This is k squared minus m squared, all to minus sign. So this is the inverse of a propagator. So I understand now how projection happens, right? By amputating the propagator eventually. Okay? So we will make more clear and then coherent next time. But basically that's where we're heading. And then eventually we will extract S matrix at this more formal level without relying on productivity for a second. Okay, so that's it for today. We will not meet tomorrow. Next Monday we will resume, and then I will let you know the rest of the plan. Okay, thanks.
코헤런트라는 게 코헤런트 스테이트들로 패스 인테그럴 곱곱에서 하는 그거 말씀하시는 거예요.